Today's seminar will be given by Danny, who is a PhD student, as you might have noticed by now, working with JWST. So Danny, she did her bachelor and master's at the Delft University in the Netherlands. Now she is with us. We are extremely happy about that, I think. So today she will tell you everything about how do you get from the detector to the spectrum, and then hopefully what you're gonna do, or how you can actually exploit that spectrum for science. Yeah? Go. The floor is yours, Danny.
All right, thank you, Andrew. I think everyone can hear me. Let me start the time. Okay, so thanks everyone for joining me. I think you can already see the title. So as Andrew said, I'll be talking about the JWST instrument MIRI and going from the detector effects and how to calibrate these, and then going to spectra and talking a little bit about protoplanetary disks, which means that this is a seminar in two parts. I will be talking about the calibration of the MRS specifically for unresolved sources, and then a little bit about water and protoplanetary disks. So let's start with the first part. I'll be introducing JWST and MIRI-MRS. We'll be talking about the detector scattering that we are dealing with, the nonlinearity in the detector along with the brighter fatter effect. I will be explaining what that is, so don't worry. Fringe correction methods, and after that, I'll be talking about my cycle 2 calibration program, which is specifically for unresolved sources. So, okay. In case you've been living under a rock, this is James Webb. It was launched now, I think, almost 2 years ago, right? Yeah, it's been almost 2 years. Time flies. So it's somewhere flying around in L2. It's got a mirror of about a diameter of 6.5 meters, and it has 4 instruments on board. Most of these work in the near infrared, but of course we're interested in the mid infrared, which is what MIRI is looking at. And more specifically, MIRI has 4 modes. So it has an imaging mode. This is MIRI, by the way, over here. So it has an imaging mode. It's got coronography, a low-resolution spectroscopy mode, and a medium-resolution spectroscopy mode. And we're most interested in the MRS, so that's the medium-resolution spectroscopy. This is the MRS over here. So if we take a little look at what it looks like specifically from the inside, the light comes in from the telescope, and there's 2 dichroic wheels over here. Each of these dichroic wheels has 3 different settings, and all of this light is split onto 4 different channels, which means that each channel has 3 different kind of sub-bands, and you need to expose 3 times to cover the full range of the MRS spectrum. So after this, all this light is then projected onto an IFU, and this is what this is over here. So essentially, this splits the light into different spatial coordinates. So aside from just spectral, we also get the spatial information. So after, right, I should go for this first. So let me quickly explain to you what a point spread function is. So a point spread function is basically, it's a Fourier transform of whatever aperture you have. So for James Webb, this is this kind of complex hexagonal pattern. So if you do this Fourier transform, you kind of end up with this, which is a very complex looking PSF. So this is, if you have a single dot on the sky, it will not be a dot on your image. It will be this complex Fourier transform of whatever your aperture looks like. So if you take a little slice through this, this is what the PSF looks like on the detector. So ideally, you'd end up with this kind of red, narrow pattern, but because of scattering, which is what I will tell you about in a second, we are actually broader. So you can see that we are, in fact, not diffraction limited. So what the detectors then look like, so this point source is then dispersed onto the detectors, right? So because it's an IFU, we've got these different slices. And each of these slices has a spatial coordinate per slice and a spatial coordinate from left to right within the slice. And then from the vertical direction, we get the wavelength. So you combine the pixels onto your detector into a cube. So you get this spatial image, and each of the pixels in this spatial image essentially has a spectrum of its own. And because the wavelengths are increasing quite a lot over the MRS, because we go from 5 micron all the way up to 28, your footprint will also increase because your PSF increases, so your resolution becomes poorer, in fact, as you increase in wavelength, which means that you need kind of bigger slices to still see your PSF. So now that we're on the detector, this detector actually has several layers, so you can see here, and each of these layers are actually reflecting at different wavelengths. So due to the efficiency, you're not necessarily detecting your photon at first pass, which means that it gets to scatter around in the detector before it's detected. Because other wavelengths of photons also come in, they kind of interfere with each other. So this results in quite a complex pattern in your spectrum. So one of these effects, it has 2 effects. One of this is the spatial broadening. So what you can see here is a point source. So because we have these different slices, you can see that your point source is on these different slices. And you can see that there's a lot of scattering over here. So that means that as I showed, your PSF is broader than you actually expect it to be. The second effect is actually spectral fringing. So aside from spatially scattering, we're scattering in a spectral direction as well. Different wavelengths interfere with each other, and you get this complex up-down kind of sinusoidal-looking pattern in your spectrum. So obviously, both of these things are not very desirable. So once you finally do detect your photon, the signal is accumulatively kind of collected onto in the data. So this means that it looks like a ramp. And ideally, you would just expect a linear increase, right? Because your flux is constant. You expect a linear increase with maybe some noise around it. So that would be the green over here. So you might maybe see some noise around this, but you'd expect it to be linear. Unfortunately, it is not. So that is what we're seeing here. It kind of bends off as you increase in signal. And the reason for this is that in the detector itself, the way that the electrons are guided down to the pixel is because of a voltage difference between the top and the bottom. So you generate a photoelectron, and it's because of the charge difference moves down to the pixel. However, as you're accumulating this charge, the bias voltage, so the voltage difference, actually becomes smaller, which means that this region where you are able to guide down your electron becomes smaller as well. So if your photoelectron is generated higher up in the layer, it does not reach the pixel. So instead, it needs to be generated lower before it is able to move down, which means that you are effectively detecting fewer photons as you move up your ramp. And that's why it starts to bend off, even though the flux is constant. So that is one of the issues. And if you think this is the only thing, then you know exactly what your ramp is supposed to look like, or kind of like how much this effect is affecting your ramp, and then you can correct it based on this. Unfortunately, we are also affected by differences in contrast in charge. So if you see this here, on the left, we have this is 1 pixel, this is another pixel, and this is another pixel, right? So you've got this charge region which is shrinking as your voltage changes. So if one of these pixels is much brighter, this region shrinks a lot quicker, which means that you get a difference in how big this region is, depending on what pixel you're looking at. So rather than just staying here, some of these electrons will actually diffuse to a neighbor because of this difference. Because here, you can still guide the electron down, but here you cannot, right? So it moves to the neighbors. And what this does to the ramps is what you can see here. So this is the bright central ramp. And because the neighbors will start to accumulate this extra charge that comes from the central pixel, they are actually moving up. So they are collecting more than is actually the flux over here. And you can see that even further from the center as well. And what this effectively does is that it broadens your PSF again. So this is not scattering, this is charge migration, and this also broadens your PSF. So you can see that here. So what you need to generate a nonlinearity correction is uniform illumination, and for point sources this is difficult because there's inherently a lot of contrast, but because of fringing, there's never such a thing as constant illumination in the MRS. So let's go to fringing next. We have two methods to correct for fringes. So one of these is just a static fringe flat. This is based on uniform illumination, well, as uniform as you can get, I guess, in space. And because of this does not actually work that well for point sources, because fringes are actually dependent on how you illuminate your lens, your detector as well. So because of this, your pupil, sorry. So because of this, if you see this kind of black dotted pattern, that is the extended fringe. The colored is what it looks like if you sample different parts of your PSF. So in the center, it looks the most like uniform illumination. But as you move away, you can see that both the phase and the amplitude change, which means that a fringe flat is actually not sufficient as soon as you deviate from uniform illumination, which is the case for most astronomical sources. Which means that there's an extra correction in the pipeline, which is the residual fringe correction, which looks for dominant frequencies in kind of the expected range of what we think the fringes will look like, and it kind of divides these out using a sinusoid. This cleans up your spectrum quite well. Unfortunately, it might also clean up your molecules, because molecules can be periodic, and they can have periods that are very similar to what you would expect from the fringes. So if you look, for example, at CO, this is a periodogram of, so in the blue, I have basically just deconstructed the frequencies of CO. So you see these different peaks. The black is after only applying the fringe flat. So in this case, there has been no frequency filtering, so the CO feature should still be there. Then the gray is after applying the residual fringe correction. And I have actually marked specific points where you can see that there's a very distinct CO peak, which is removed after the residual fringe correction. So what you're doing is you are altering what your feature looks like. And I have an example of this here on the left. So the pink is no residual fringe correction, and then blue is with. And you can see that certain features that are part of the CO feature are kind of lessened or removed, in fact. And this may not seem like a lot right now, but when you are trying to determine what the excitation properties are of your CO, you want all these small features as well, because they tell you what your column density is, how it's actually excited, and what the temperature is of the gas. So this is very important, and this actually changes what kind of properties you derive from this. So this brings me to, to a way to fix these kind of problems, specifically for unresolved sources, because unresolved sources are very repeatable. They look the same every single time. And fringes depend on the illumination pattern. So what if we use a kind of boring reference to extract the fringe pattern and divide them out? So you can see that over here. I've used a boring A star. You might find them interesting. I do not. So you can see here in the dotted line is the original kind of fringe pattern on the detector, and then the colors is after we divide this out. So you can see that it does a very good job. So we apply a reference, an A star to a G star. So it's two different sources, but they are on the same part of the detector, and it works very well. Unfortunately, it is quite sensitive to if you are slightly offset from exactly where your source lands. So we see this here. This is the offset in milliarc seconds. This is all much less than a pixel, by the way. So your pointing needs to be super accurate, because as soon as you kind of hit this 30 milliarc second range, the fringe contrast actually just shoots up. So it does a much worse job if you're not exactly in the same position. This, by the way, is what the fringes look like if you just look on the detector at the different contrast, and it's kind of like a zebra pattern situation. If this was an extended flat source, this would be straight lines. So this also shows the phase difference. So this is how we would make use of the pointing repeatability. But even with target acquisition, which is not necessary usually for extended sources, blind pointing is fine as long as you fill in your coordinates correctly. But we do need this pointing repeatability to be able to use this fringe correction. Unfortunately, even with target acquisition, it's not as repeatable as we want it to be. So this is all of the pointings in offset from cycle 1, so all of last year. And this is where you would expect it to land at a 0 offset, and this is the distribution of where things actually landed. So we can see that, like, for 85%, this is within 33 milliarc seconds. After that, there's a couple more. But what this means is that at this point, your fringe contrast will already increase if you don't land in the same position, right? So that means that for these cases, they can be quite unlucky. And for them, there might not be a good reference available. So to fix, I guess, this problem, we proposed for cycle 2 a sub-pixel raster of a star that's relatively well known to overcome these repeatability issues. This is what we wanted. So these are the different dither positions, which is what a point source will always be landing on if it's with target acquisition. And then we kind of do a sub-pixel raster so that even if you're slightly offset from this dither position, we can still have a good reference. This is what we wanted. This is what we got. This was 3 weeks ago now, I think, from the top of my head. So we got all our data. And this is, I find this quite impressive, right? This is a giant telescope in space. And we're doing pointings within a pixel. It's tiny. It's a really, really, really small variation, and it does it quite accurately. Aside from the fringes, though, I talked about how these ramps look, and the way they look depends on the contrast. If you repeat the exact illumination, the ramps should also be repeatable. So these are the ramps from the data that we got, and you can see with the different offsets, because the way you're sampling your PSF changes, the contrast slightly changes between the pixels. So, for example, we've got this case here. So all the solid lines are from the same data, just with different pixel offsets. So this is the central pixel, this is an offset, and this is another offset. And then the dotted lines are from the same data set, etc. And you can see that here we have a very bright central pixel, so we're closer to the center of the PSF. And then the offsets show quite a distinct BFE, brighter, fatter signature, because they're really pulled up. Similarly, here, the illumination, these 2 pixels are probably on either side of the PSF, so their contrast is a lot less. And in that case, the BFE signature is also a bit smaller, because there's not as much contrast between the different pixels. However, because this should be repeatable, we can just get a correction per ramp, per pointing, and apply this to other sources that also land slightly offset. So we can kind of fix this broadening of the PSF and get more accurate flux calibration out if we know exactly what the ramp shapes are for specific pointings. So as I said, you need this flat illumination, and I already said that there's no such thing as flat illumination for the MRS because of fringing. And here we're demonstrating the fact that the ramps do really change depending on whether you're looking at a fringe peak or a fringe trough. So these are, again, the different pointings, and instead of showing just the raw ramp signature, we're looking at the rates instead. So I've just taken the difference between the different frames, and this is what you end up with, right? So what you're expecting from the nonlinearity is the fact that this rate decreases quite steadily, right? So that's what we're seeing for the brighter ones. On the edges, because you are slowly gathering more electrons, because there's this contrast difference and they're migrating, you slowly get pulled up, right? So that's what we're seeing here. However, we're also seeing a difference, because if you are at a fringe peak, you actually kind of lose your signal much quicker than if you're at a fringe trough, because there's a difference in contrast. Similarly, so these are the center ones. And then similarly, if you're looking at the wings, you also see that the ramps actually have a different shape, depending on if you're looking at a less illuminated or more illuminated pixel of the fringe pattern. So this also becomes more important just for the fringing alone. What about semi-extended sources, though? Because we've only talked about unresolved sources, and it is an IFU, so presumably some of these sources will be more extended, and we do see this. So there is the problem with these is that for extended sources, they're much more complex. It's not always repeatable, right? So you can't just put a reference source on there and expect the same thing. So fringes for a point source seem to be predictable from the ground. So this is ground data. So you can see that depending on which part of your PSF you're sampling, you kind of have a steady change in depth and phase, right? I mean, there's some scatter, but there are some trends. And since extended sources are just the combination of multiple point sources, you should be able to use this to reproduce the illumination of whatever you're looking at, and also the fringe pattern. Sorry, I'm getting an update request. Okay. So this brings me to the full plans of the cycle 2 data, because we've only had it for a couple of weeks. We have multiple plans with this. So it's not just the fringe corrections, although that's one of them, and the ramp corrections. So firstly, we want to just create a library of pointing-specific ramp solutions, as I said. Secondly, we want to create a library of these fringe corrections. With this also photometric calibration. But some of the more future goals are also really sampling the PSF very well on the detector, such that we can extract spectra from the detector directly, so we don't have to average things out by building a cube. And finally, as I said, there's forward modeling of the fringing to also correct for resolved fringe patterns. That's what my last point was. Okay, so all of this is needed to get the best data out possible, because we don't just care about these very bright, very easily detectable features. To be able to do what we want to do, which is characterize molecular emission really well, we need the small features as well. So don't think that this is a completely separate part. They're actually very much connected. So that brings me to water in protoplanetary disks. So let's get started on part 2. First of all, I will give a little bit of an introduction to what protoplanetary disks are, what they look like, what we kind of expect from them. I'll be looking at what we see specifically with MIRI-MRS, also the water chemistry and how this is excited, so why we are seeing the lines where they are. I will be showing a spectrum of one of the disks that I looked at specifically, which was SZ98. Then some of the work that I've been doing now, which is trends with what the outer disk structure looks like and what we're seeing in the inner disk. And then finally, what the implications actually are for planet formation, which is probably one of the ultimate goals, I guess, of understanding protoplanetary disks. So what are we looking at? This is the evolution of how we get to a planetary system, right? We start with this molecular cloud. This slowly starts to kind of collapse. You get a protostar, which is surrounded by a giant envelope, so you can't really see the star. At some point, it is dense enough to start fusion, and that's when we hit the protoplanetary disk. So there's a disk of dust and gas around this young star, and then eventually this disk will dissipate, and the dust will clump together and accrete, and you get these planets. I'm specifically going to be talking about protoplanetary disks, and because you're all stellar astrophysicists, I'll put it on an HR diagram. I won't be talking about any of these today. I'm talking about the part before. So this is a little evolutionary track. We're talking about pre-main sequence stars. Specifically, I will be talking about more intermediate mass, so they're a little bit more solar type kind of precursors. And the luminosity is important. There's a couple of driving processes that kind of dictate what a protoplanetary disk will look like or what the emission will look like. And one of these is stellar luminosity. So if we go up in stellar luminosity here, because basically the irradiation is less, the temperatures are a bit lower. So this means that here, the lines where the ices on the dust become gas move inward, right? So this is a very luminous, these are usually the Herbics, they're very luminous. They have a lot of irradiation on their disk, the temperatures are high, so these ice lines are further out, and as you move down in luminosity, they kind of move in, right? So these are kind of very low mass, brown dwarf kind of objects, and these are the intermediate mass objects, and that's what we're looking at specifically. A second process that's very important is the dust evolution. So as you go from this envelope to disk phase, so the disk is now kind of flat, but it still has this kind of vertical profile in terms of dust. So the first thing is radial dust drift. So as your dust clumps grow, they get some gas drag and they start to move inwards. The second thing is dust trapping. So if you do get a protoplanet, this is more massive and it's able to carve a gap in your disk. What happens is that it actually prevents some of this drift. So you get these dust traps that trap these icy pebbles, for example, in the outer disk. And finally, there's dust settling. So the dust will slowly kind of move to the midplane and not be as vertically dispersed, I guess, in the disk as much. So these are some important processes to keep in mind. In fact, with ALMA, we can really see this dust very well, and we see that there's a huge diversity in what the disks look like. So for example, this is the disk I'll be talking about later. It is one of the largest, it has one of the largest dust disks in its star-forming region, which is Lupus. And it also has some gaps, some substructures, as you can see here. Similarly for GW Loop, it's generally got a full disk, but there's some substructure here. IM Loop has spirals, and some of them are too small to resolve. So there's a huge diversity. Unfortunately, well, maybe not unfortunately, what we see with MIRI is a blob, right? Because we're at infrared wavelengths, we're very high in the sky, so we have a very small, well, relatively smaller collecting area. So you end up with an unresolved source for most of these disks. So we just extract a spectrum from the blob. So we don't exactly know spatially where we're looking. This means that there's a difference between a face-on and an edge-on disk. If you're edge-on, you're looking through the disk, and you get absorption features. Some of these absorption features are actually ices, which are further out in the disk. So that's very interesting in itself, but I'll be mainly looking at face-on disks. And in this case, you're seeing emission features. So you're seeing the combination of the inner disk, because the star does emit still a little bit in the near IR, but this kind of basically completely disappears, right, in the mid-infrared. So I don't care about the star, only the influence it has on the disk. The mid-IR is a very interesting region because we're seeing this very dynamic inner disk. There's, you're quite a little bit before the H2O snowline, and then after this you get the sub-millimeter at much larger distances from the star. So, right, because we see the entire inner disk at once, we don't exactly know where every single feature is coming from. There's also, because the large variations in temperature and pressure, both radially and vertically, there's a lot of chemistry going on. There's a lot of complex features, and of course we don't exactly know what we're tracing. Secondly, it can be highly irradiated. So this means that there is also photodissociation, which I will talk about in a second, but that's essentially just destroying your molecule based on the irradiation of the star. And finally, because we're looking kind of through this disk, there is an optical depth limitation related by where your dust is, but also how dense your gas is in that specific wavelength. So if you have a very dense layer of water, you can only see up until the optical depth. You don't see further down. So it could be that it's even denser than what you're able to see, but you can't always trace this. Furthermore, because this environment is so dynamic, there's a lot of irradiation and higher temperatures. Whatever ices come in from the outer disk and then sublimate into gas, a lot of this is immediately recycled because of the high temperatures and molecules being destroyed. The chemistry kind of resets itself. So let's talk about the life cycle of water. There's a couple of things here. So first of all, I talked about pebble drift. So you have these icy water pebbles. They're moving inwards, and they cross their respective ice line, and the ice is released in form of gas into the disk, right? After this, the gas is reset by, for example, photodissociation or thermodynamical processes. If it's destroyed by photodissociation, you have your water here. This becomes OH through photodissociation, and this this can react again to become water if the temperature is favorable for this. If you have a lower temperature, it in fact will become CO2. So there's a difference between what temperatures and what layer you're at and what kind of reaction is favored, and if you'll be seeing more CO2 or more water. So you formed your water. Now it needs to be excited so that you can see it. So we have in the near IR and the mid IR, there's essentially two motions of the water molecule that you can see. So this is rho vibrational water, so it's vibrating and rotating. And then there's pure rotational water, which is in longworths of 10 micron. Pure rotational water is what I will be talking about most today. And this is mainly excited through collisions with the hydrogen molecule. So it gets to an excited state, and then as it decays, it emits a whole ladder of water lines at different wavelengths. So it decays to the ground state due to collisions or emission of photons. And usually for the rotational lines, you can assume that it is in local thermodynamic equilibrium, which means that the excitation and the decay are kind of balanced. And in that case, whatever you're tracing as a gas temperature is actually, so as an excitation temperature, sorry, is actually equal to the gas temperature, which is very nice, because that means that if we get our properties from our emission, we know what the gas temperature is. So this assumption is more accurate usually for the rotational lines because they have a lower energy and a lower critical density, which means that you don't need to reach very high pressures and densities to excite these lines through collisional excitation, whereas for the rho vibrational water, this is very high energy and usually has a different mechanism of exciting it. So finally, the actual strength of these water lines is related to several properties. So each of these dots is an individual line in the spectrum. So here I'm showing the wavelength with the Einstein A coefficient, which essentially tells you how bright it's going to be. Here we also have the upper energies, which tells you kind of if you're tracing a colder part or a hotter part of your disk. And then finally, we have the upper and lower levels. So lines in general become stronger with an increase in temperature, an increase in column density, so that's essentially how much of this water you're seeing, and secondly, with the emitting area. So in general, if your column density and your emitting area increase, it just linearly goes up. Everything goes up at once, right? Especially with the emitting area, this is mostly true. However, for the column density, this can be a little bit more complex. So firstly, because with increasing wavelength, you are essentially probing kind of colder lines. They have smaller critical densities, so that means that they're more easily excited if the disk is less dense, so you're kind of naturally tracing an increase in radius and a decrease in temperature with wavelength. So that's the first thing. Secondly, if you have the same upper level for two lines, but a different lower level, so you can see that here, you've got lines that are on the same line in terms of upper level, but their lower level is different. That means that one of them will be opaque or saturated sooner for certain column densities than the other one. So as your column density increases in a specific region, because if we're in the same upper level, they're expected to be emitting from the same region because they're excited the same way, then you would expect the line with the lower level to still increase, but the other one is saturated. So it can no longer go higher, so that one stays constant, So if you know the ratio between these two lines, you can trace how much water is in a certain region, if that makes sense. Each of these lines also have different temperatures, as I said before. So because of that, you can trace how much water there is in a hotter region and how much water there is in a colder region. So now, because of MIRI, we are able to see individual lines. So I will be showing that in a second, but first I will talk about what data I'm actually using. So we're talking about the MINES Guaranteed Time Observing program. So the people who contributed to the instrument development back in the day, they got a certain amount of time allocated, and they divided this amongst different topics. So I know there's some people here who work on the exoplanet GTO. There's also one for disks. This is the MINES collaboration, and it is, the PI is Thomas Henning. And there's in total 51 sources in this program. I think there's 140 hours allocated to this, if I remember correctly. A bunch of these are Tauri stars, which is what I will be discussing today. These are the kind of more solar-like pre-main sequence. There's some brown dwarfs, so these are very low luminosity. The split between very low mass and brown dwarf is a little bit vague, though. And then there's a few Herbig stars, then they're very, very bright. Won't be talking about these. So let's show a spectrum of a Tauri star. This is what it looks like. It's pretty typical. So this is the Spitzer low resolution at the bottom, and then this is the MIRI spectrum on top. And we can already see there's a lot more going on in the MIRI spectrum, right? It looks like a lot of noise, but in fact, these are all features. So this is the rho vibrational water, a little bit of CO over here that we can see at the shorter wavelengths, and this is all rotational water in the longer wavelengths, and we can see this huge difference between what we were able to see with Spitzer before and what we can see now. Of course, this is low resolution Spitzer, high resolution Spitzer, slightly better, but you could not see the rho vibrational lines in high resolution Spitzer. So this is great. We can see a lot of individual lines, and we can very clearly see, look at ratios of different temperatures and different column densities based on these lines, right? If we zoom in on this, this is a big part of the spectrum, and it's a huge amount of features. So this is, again, rho vibrational water. Here we have all of the rotational water. So firstly, I said that you're naturally tracing, kind of moving inwards to outwards of the disk, right? So we did some kind of very simple 0D fits per region for the water, and we are in fact likely tracing lower and lower temperatures and further and further radii as we are moving outwards in wavelength. There's a second thing that we can see, and that is the carbon-bearing species. So we've got the CO2 feature here. This is HCN, and this is in fact a lack of C2H2, which is interesting because if we look at another disk that was examined by Sierra Grant over here, GW Loop, this is a very strong CO2 feature, much stronger HCN, and there is C2H2 present, which we cannot really see in as at 98. So you can see that difference here. This is massive compared to the water lines, and here it's much smaller. So there is a diversity here. This diversity is not necessarily new. We already saw this with Spitzer. There were trends that were already discovered here. So but the resolution and sensitivity was too low to look specifically at specific lines. But they looked at line blends and fluxes specifically, and there were a few trends that they could see, which is, first of all, your HCN over H2O ratio seems to go up with an increase in disk mass, and similarly with the outer dust radius. An increase in outer dust radius essentially means you have less water and more carbon-bearing species. Seems to be the trend. This is likely related to drift. So as I said, these icy pebbles drift inward, they sublimate and create water. So that if you have a full disk, this can freely happen and you would get a lot of water in your inner disk. However, if you have a gap, this would prevent this drift and trap the pebbles, and this wouldn't happen. That's the theory. So how does SZ98 fit in? It has one of the largest dust disks. so it's not radially small, and it has a disk with multiple pressure bumps. So it seems to not exactly follow this decrease in decrease in H2O over HCN with this outer dust radius, because it's big and it has pressure bumps, so you wouldn't expect as much water. However, now this radius relation has also been seen with MIRI, JWST. So here they actually specifically, because we can probe individual lines now, they specifically looked at cold water, because cold water is expected to be much brighter due to drift, because there's diffusion of this cold water across the water snow line. So you would be able to see the signature in brighter cold lines. And they do see this. They see that low energy versus high energy water, this decreases as you get a larger dust disk. So, and that dust disk would be tracing drift, right? So they see signatures from this already. But I think we should also look at the gaps, and that's what I've been doing, because even with gaps, we can still see that there's quite bright water. And in fact, there seems to be a bit of a tentative relationship to where this gap is located. So the closer the gap is to the star, it seems to be that there will be more water, so it might be less efficient at blocking drift, or there's something else going on. And we can see this both for the cold and for the hot water. So this is the hot water, and this is the cold water. And we've got the gap radius on the x-axis. And then this is the column density, which also goes down. There are a few interesting outliers here. And this is just the general line flux. And because the general line flux always goes up with radius, and this here we're tracing the column density, the only thing that if you divide these two, you would be left with some kind of radius, emitting radius proxy. So this also seems to decrease, but there's definitely some outliers that need more looking into, and if this does make sense. Another thing is, so the further out the gap, the lower the water flux seems to be. Exactly what this is related to, I'm not sure yet. So it could be that this is less efficient, or that it needs to be deeper to trap the same number of pebbles, so it's less efficient at stopping drift than a gap that is further out. And there is some evidence for this being the case, but it's a bit tentative right now. Secondly, if we look at the carbon-bearing species versus the water, you could kind of be tracing what your C over O ratio is, right? So we see that in basically all the cases for the cold water, the ratio between the carbon-bearing molecule and the cold water also increases with where your gap is located. So this again seems to kind of trace this drift scenario, especially because for the hot water, there seems to be a smaller correlation. This is all still in the works, so I'm not exactly sure yet, but especially for CO2, there seems to be quite a difference in this relationship, right? So it could be that this change in C over O ratio is correlated with the gap, where the gap is located, but also it might be stronger with the colder water lines, which would point to this also being related to the drift. So finally, because gap formation, it's not always caused by planets, but it's definitely one of the most favorite explanations by people. So what does this mean for planet formation? So aside from seeing this in the inner disk, which is what I've seen, Nienke van der Madel also saw this happening with gaps in the outer disk, that there's changes in C over O ratio if you have a gap. So this means that the presence of a planet further out in your disk can really influence what your planet will look like further in, right? And this might have been the case for what we've been looking at here on Earth, because we have Jupiter out there, which could have been carving a gap and changing whatever was available for accretion in the inner disk for Earth, right? So you start with a certain kind of a C over O ratio in your disk, you form a planet, you trap whatever is present on either side, and this affects what is accreted onto your planet and what their final C over O ratio is. So to conclude, the MRS is complex, and we need to understand it properly to be able to really get the best spectra out so that we can look at these line ratios and have them accurate. Illumination-specific empirical solutions work best. They work really well. Unfortunately, they don't work if you have something that's resolved because it's much harder to reproduce. But there are some solutions that might be possible that I'll be looking into. Similarly, protoplanetary disks are very diverse. And the dust disk structure in the outer disk does seem to have a relationship to whatever is happening in the inner disk, so in the terrestrial planet-forming zone. So we cannot just look at these separately. There needs to be some kind of connection. And a massive outer planet could have influenced whatever was happening in the inner disk, which could be like Jupiter and Earth. And that's all from me. Thank you.
Thanks, Danny, for the wonderful talk. I mean, the amount of jokes we made in the corridors about that brick possibly never flying and Jarnis losing his job was immense. But finally, we see all the great results coming from the James Webb and intelligence put into the interpretation of the data. Thank you for that. Time for questions, comments, whatever you guys prefer.
It's all wrong.
Come on. So the instrument gurus and all the protoplanetary disk gurus.
Hi, Danny. Nice talk.
Hi.
I was just wondering, what's a pressure bump and what causes it? You showed a plot where you could see like a bump, yes.
Yeah.
But how do we know that? I mean, what is a pressure bump? I guess. Like.
So a pressure. Yeah, I guess this is an okay image. Yeah. So a pressure bump is basically the ring, right? Yeah. So this is where it's all kind of collected and this empties out a gap. The thing is that there's many things that could cause a pressure bump, and there's a whole list, there's a whole review of different processes that could be related to the magnetic field, could be related to other physical processes, and of course one of them is a planet forming the gap. But this is quite difficult to confirm because you actually usually need to see it. There's PDS 70 where you see 2 protoplanets. But there's a much larger gap there. So there's a lot of, and the pressure bump itself is basically where the dust is being collected. So this is all millimeter dust. It might be that there's some gas in between, right? But the dust itself is kind of trapped in this pressure bump. Does that make sense?
I think so. So the dark ring, yeah? So the dark ring is not an absence, it's actually a concentration?
So so this is the larger the millijansky per beam, the brighter it is in millimeter emission, which means that the brighter it is in dust, right? The more dust there is. So here actually, SZ98 is often referred to as a fried egg because there's a lot of dust concentrated near the center. So the black is an absence of millimeter dust. And the pressure bumps themselves are the rings.
I see. So I had it flipped around.
Yeah.
Got it. Cheers.
More questions? Yep, Mariam.
On slide 33, you had a series of plots, and on the bottom was a plot describing upper and lower. Could you just talk a bit more about that? Because I wasn't sure if that was like spatially within the disk or what.
No. So this is specifically the excitation parameters or properties of specific lines, right? So these are all specific lines. So each of these lines has a specific upper and lower level. And this kind of relates to also with the Einstein A coefficient, it dictates how bright it will be. It dictates like what does it saturate sooner when there's a lot of it. So it's really the properties of the lines. And I must say I'm not a chemist. So if you want the specifics, I don't really know.
Okay, that's great, thank you.
So in the first part of the talk, you showed that depending on how you change how you're responding to the light that hits the beam, you can mask out some of these lines completely. or maybe
Sorry?
I'm describing that badly, but you had sort of the CO line, you were able to kind of remove that completely, just depending on how you process the data. And then on that slide that you just had, 33, you were talking about how the science is really heavily dependent on the ratio of different lines.
Yeah, that's exactly why you need to really think about how you're correcting your fringes. So for the ratios that I showed, actually, I did run this algorithm because unfortunately, a lot of the MINE's data that was taken later is not taken with target acquisition. So because I said they have like 140 hours they had allocated, so they tried to do as much as possible. And I think for some of these, that meant not doing target acquisition because it takes a little bit of time. So that means that it's harder to run that. You can't do the fringe correction as well with the reference because you're not exactly in the same position. So that's an issue. So I did run that algorithm on the ratios that I showed. I actually plan on looking at how much of an influence did that have, because some of them are taken with target acquisition. That's the case for SZ98. So the spectrum that I showed was in fact with my way of correcting the data or calibrating the data. If I can find it. There we go. And actually you see that this seems to be a little bit noisier than some of the outer parts because this is a silica dust feature, so the features on top of that tend to be a bit sparse. So a lot of these wiggles, I hate the word, but a lot of the wiggles are actually fringes because in channel 2 there seemed to be a slight offset between the reference that I use and whatever was happening with this observation. So this is actually slightly noisier because of that, but I did not run this residual fringe correction because I was worried of it changing whatever I got for the excitation properties because we specifically fit the lines, right? So does that make sense?
But
yeah?
if you add in that residual correction and you completely remove a line, doesn't that completely change the science of what elements and compositions you're measuring in the disks? My question is, how much can we trust the detection of any particular element or something in a disk if just changing this PSF correction can wildly change the peaks and the ratios that you're measuring?
Yeah, so wildly changing is probably not quite right. It's quite subtle changes, right? So, and specifically, you need this periodicity to be in the range that you expect for fringes. So for CO, and I presume the row vibrational water actually, this is a lot closer because it's quite small, there's quite small spacing. Here, this actually becomes a lot less. So I think there, the frequencies do not match with the fringes as much. What's much worse actually is hydrocarbons, because hydrocarbons have a very nice sinusoidal pattern that is very similar to fringing. So I think, but again, I actually plan on checking this because I had this thought this morning that, hey, maybe that's what the scatter is. So I will be checking this. But I think that for these lines, because they're a lot more spaced, they're not as periodic as here for row vibrational water, that it doesn't matter as much. And I'm looking at the rotational water only.
Thank you.
But no, that's definitely a good point, yeah.
Hey, Danny. Thank
Hi.
you for the talk. I was wondering, is there in the future some detector effects that might also impact your work? So I'm not very familiar, for example, with normal detectors, only CCD detectors in general, but they're very different, as I know. And for example, the charge transfer inefficiency, would that be a problem in the future because, well, you're in space, right?
I mean, oh, you mean so how it's going to develop?
Yeah, exactly. Yeah, so
yeah.
like.
Funny enough, we have a response drop in MIRI. It's actually, what is it, 30, 40%-ish in the longest wavelengths since launch, start of operations until recently. So depending on the wavelength, this drop is larger. It's happening everywhere, which is a bit of a misconception sometimes, but it's really the largest in these areas, like it really bends down, which is a bit of an issue. So there's more noise then. We don't know what it's caused by, and we also cannot talk about it.
Perfect.
Yeah. If there is a red dot on my head, you know what it's caused by.
Thanks for the talk. I have another question, but with respect to CCDs, the fringes are very wavelength dependent. So if, depending on which source you illuminate, your fringes will differ. Is that also the case in MIRI? So that means that you use an A star to calibrate the fringes? Is it different for an O star or for an M star, whatever? No. So there is no wavelength dependent.
There is wavelength dependent for fringes, but we are looking at the same wavelengths regardless, right?
Yeah, but
so
I mean the illuminating source has a slope.
It just makes it more difficult. So there's actually a bit of a there's a thing going on right now. So there's some people in the US who have in fact used asteroids to do the same thing. The thing is, they're not working on the detector though, so they built the cube after, and because you're kind of averaging out separate pixels, your fringe pattern becomes less dependent on the pointing, I think. It's still important to do target acquisition, but because asteroids are a lot redder, you get a lot more signal. We, in fact, do not get any signal, well, basically none, for stars in this region. So that's actually why this is, you can see that very clearly here. For my calibrations, it's quite noisy, but this is what we had at the time. So now there's some work being done with asteroids, and that, of course, has more signal, so there's less noise in your corrections. The problem with asteroids is that they're only good relative calibrators, flux calibrators, because there's rotation. They have a lot of morphology that changes how bright they are depending on what time you're looking at them, so there's a bit of that. And
they have features, no?
They also have some features, yes. Yeah. But in general, they're quite well fit with a black body. I'm also, to be honest, I'm not super sure what the features look like and how much they impact the fringing, because I didn't do the work. I don't actually know how much that, I haven't looked at it, to be fair, but I think they do say that it's relatively well fit with a black body, and I don't know if they remove any features.
Okay, thank you.
All right. I think we need to stop. We're at the hour. So let's thank Danny again. Thanks. Enjoy your lunch and see you next week.